What's up guys, Cyprien here and welcome in this next video of the series Analyst 101 on scale mode, and we'll talk about pressure loads today. So pressure loads in on scale analyst can be simple, but they can be also complex depending on what kind of shape you want to apply the pressure to. So the first thing you need to know is that to comment the pressure loads, you'll have to use the plot commands. So the plot commands can be used to assign a pressure to a specific set of nodes according to various orientations and shape. So you can look at those different pictures. You can assign it to a side of your model, you can assign it to a specific circle geometry, you can assign it to a cylinder or a sphere, and I'll show you a few examples of how to do that. Now, first of all, you need also to have a driving function to go with this pressure load, because this is a dynamic type of analysis. And if you don't know how to define a drive function, well, I refer you to the previous videos I made in the series, which talks about drive functions extensively. Now, let's continue and let's have a look at the first type of pressure load, which is a simple wave applied from side to a model. So this is really the simplest examples to begin with. And we see that this command here has three subcommands, which will allow you to basically assign this pressure load to this side of the model. So what those commands are, well, let's have a look at that. So first of all, you have the subcommand pdef, pressure definition. You can call it like this, and this command takes two parameters. One is the plot name. So this is a name that you can define by yourself. Whatever you want to call it, you can call it like that. So in this case, it's called PLD1, pressure load 1, right? And the second argument is the driving function that you have defined into your code. Now let's have a look at the second subcommand, which is the vector subcommand. So this subcommand also take a name that you can define for this custom vector, and this vector is used to define the direction of the positive pressure vector. So basically, if this is pressure coming from left to right and it should be positive, then the vector should be 1, 0, 0. And the last one, the SDEF, is basically surface definition. That's why it's called SDEF. This is where you tell it, to which kind of nodes will you actually apply this pressure. And so this takes the name of the pressure definition here, so which has the drive function assigned to. It takes the vector, which will give it the direction of the pressure, and it takes the surface definition. So the surface definition is defined using key points here, and you see that in I direction it's basically a line because it goes from I1 to I1, so it's just one position. And in J direction it goes from the key point 1 to key point 3. So in the example I'll show you, the key point 3 is basically the end of the model, so this defines the whole edge of my model. Now, if I wanted to apply that in the opposite direction on this edge here, I would have to change the direction of the vector, so -1, 0, 0, and I would have to change the surface. So in this case, it wouldn't be I1, but it would be the last key point of the grid, which is usually called IND grid in your code. But it can be called anything. It depends on your code. So this is just an example for you. Now what you have to be careful also is that if you assign a pressure load to the edge of the model, the boundary at this edge should be set to 3. So if you have an impedance or absorb boundary here, for example, you cannot apply at the same time the pressure load, right? Otherwise it would conflict. Okay, and now we know that to apply this kind of pressure load, let me show you example of code in which this is actually implemented. So here I am in OnScale Analyst mode. I have retrieved the script that I used in, I think it was the video 4 or 5, where I was showing you how to assign a circle geometry, for example. So I took this one and I'm using it as a base to show you how to assign the simple pressure load. So let's have a look at this. So this case, the first part here is defining the key points and the key coordinates. Then I have the definition of the grid. Then I have the geometry. If you don't understand what I'm talking about right now, you should really come back to the previous videos of the series, because I'm going much in depth on what all this means and how you create the geometry and all this. So I will not come back on all this in this video. Then you have two materials which are essentially the same except the name. So I'm just basically creating two materials with different names. And I am using the assign command to assign the material to the grid. So I'm using region steel to set up the whole grid into steel material. And I'm creating a circle which will be in steel 2 material at the middle. So for the first example, I will assign the border of the material, so I won't actually care about the circle, but you'll see in the example afterwards that I'll use this. Let's first have a preview to see what the model, how the model looks like. So it's just a steel plate with a small circle at the middle, right? And here, right, I have done all this geometry setting and material settings and all that. I have to define the driving function. So it's here, it's a recurve wavelet. So the instruction is func wavelet. This is the frequency and this is the amplitude. And here comes the pressure. So this is exactly the definition that I was giving you before. And because I made a preview in the variables here, I have now able to look at the key points of my geometry. So I can look at the actual x1, x2, x3, which are defined as 0, 0, 0, 5, and 0, 1. And same for y. So I have a plate which is of dimension 0 to 0, 1, basically. And the key points associated to that are basically, I have 1,000 elements per 1,000 elements. And the I2 and J2 refers to the middle of the plate. And the I1, I3, J1, J3 refers to the boundary of the plates, basically. So if I look at the plot here, I have the P definition, which takes a name, the driving function that I define here. It takes the vector for the orientation of the pressure. And the surface definition first takes this, the pressure definition, then it takes this vector here. So it uses the names that I defined before to use that. And then it takes the definition of the surface, which is basically the left side of my plate. Now the rest of the code is just basic calculation. So I have a calc command which basically in which I write that, okay, I want the acoustic pressure and I want the maximum of the acoustic pressure. The PRCS command is here just to check that everything is set up correctly. So it's a required command, it's always here. Then I have a procedure which basically executes 20 loops every time, and at every loop it will basically make up an acoustic pressure plot. Then I executing this procedure 20 times, so 20 multiplied by 20, which means that in total I have 400 time steps in this simulation. And at the end I'm saving the data to the field data to a file. Okay, let's have a look what happens when I run the solver. Okay, so you see that the pressure has been assigned to the left side, and it's basically now it's updating, so it will calculate like that 20 times. Now let's talk about how to generate a spherical wave. This is slightly more complex, um, but it's very important to know how to do this. So spherical waves use two different types of commands to actually define the center of the wave and define the application surface. So in this case, the commands are still, this is the PLOD for the pressure, right? The first command is still pdef, pressure definition, is the same. The second use spot. So what is a spot? Well, the spot is a subcommand to identify a surface of nodes to apply a normal pressure loading by simply imputing a known nodal position close to the surface. So what you should understand is that you should already have some kind of surface here, and this position that I'm giving into the spot should be inside the surface you want to assign the pressure to. So it's a way to locate surfaces using a bit more advanced method. So, and then the SDF2 method, it takes the pressure definition, it takes the spot, and then basically the pressure is assigned not using key points, but using the difference of two materials. So you saw in my previous example that I'm using steel and steel 2, which basically are the same material but with different names. And when I feed that to the SDF2 command, it's what it says basically is that, okay, you will assign the pressure to the edge, which is defined by the difference of those two materials. So let's this is an example of code. So you can, if you want, you can stop the video and try to rewrite this code and try it by yourself. But let me show you in live what it does in OnScale. Okay, I'm back into OnScale Analyst, and this is basically the same code that I just shown you previously, except that this time I will use this circle geometry that I have defined to assign the PLOD, the pressure load, to it. So the geometry, we can preview again if you want, it's still the same model, except that this time I'm using the spot. And you see that I set up the key points. Sorry, this is not key points, this is a position. So position is x2 and y2, which refers to the middle of the plate. So this point here will fall right in the middle of my center circle. And because of that, the spot will basically select this circle. And this will at the same time orient the pressure towards the borders. So you can think of the spot as some kind of light going down to a specific point, and then setting up some kind of normal axis to this. Then you have the SDF2 command, which is set up using pdef, spot, and the difference between those two materials. And that's the only change I did. So I just changed those two comments from the previous script. Now let's have a look at what happens if I run the solver. And by the way, you can also run it on the cloud, of course. And now you see that the pressure is assigned to the center, and it propagates from the center towards the borders. Now, to get a very good circle like this one, your mesh should also be small enough. So if you remember, I have 1,000 elements. So it's if it was too coarse, maybe it wouldn't be so smooth. So you have to be careful about that. Now let's look at another more advanced type of pressure load, which is cylindrical pressure load with the command PLOD-CYLN. So this basically takes again the PDEF, the spot, and the difference here is the CYLN command. So the CYLN command will be found into the site command where this will be used to create this, and then in the plot like this. And so this command is not exactly the same in the site and in the plot, so I'll show you a bit the difference after that. Now let's have a look at all the arguments that this command takes. So it takes first the P definition, the spot. The SNTD means standard reference axis is used. So if you had your own axis, you created your own orientation axis, you can define it here and say, okay, I want to use my own axis. Now here we use the standard, and we want the Z axis, so the cylinder will be oriented towards us, towards the screen. And the 0, 1 you see here is the length of the cylinder. The position here is the position of the center node of the cylinder. This is the radius, and at the end, this is the start-end angle, because like you see in the picture here, it doesn't have to be a full circle. It can be just a portion of a circle, which allows you for a bit more complex type of shapes. So let's go back in Analyst, and you see that I changed that. In the site command, I basically commented out the circle 2D that I was using in my previous example, and I replaced that with the CYLN command to create the cylinder at the middle. So this time I'm using void as the material to create a hole in the middle. So I'm using standard z-axis. This is the length of the cylinder. This is the center, the radius. And you have two times. You have this command here and you have this command here. There are some slight differences. So for example, here it takes 2 times the radius. And there is also the 2 zeros here. And two angles. So if you want to see exactly what this means, you can go for the help. You have the detailed description. So this basically creates the geometry. So if I preview the model right now, so you see that instead of having a full circle at the middle, I have a cylinder with a certain angle cut like that. And here now in the plot, I'm basically using the command that I just described before. And this will, let's see what it will actually do when I calculate. Now you see that the pressure is coming from this from this part of the cylinder. It's not generated here. So this allows you for more complex shape of devices, because it really creates a pretty complex shape for your pressure load. Now to show you that it's not only in this orientation, the CYLN command can also be used by changing the axis in different orientations like this. So what I did is basically I took exactly the same than previously, but I changed the axis here. So instead of Z and having oriented towards me, I am using the y-axis, so the cylinder is oriented towards the y-axis. I changed the dimensions of the cylinder. So you see dimension goes from 25 to 75 millimeter. And then I'm able to fire a pressure load, which will be generated by two sides of this cylinder. Let's have a look. So it's the same than the previous, except that I changed the y-axis and the data. So in this case, the angle is not really important. So now you can see how the pressure wave is generated from both sides. Now, if you're wondering just why this pressure wave has two blue components and one red, this is totally defined by the driving function. So here it's a Rico wavelet. So if you would recognize the profile of the Rico wavelet, which is in time domain, which has a peak at the middle and two negative pressure on both sides. That's why it looks like this. Okay, so now let's look at another type of pressure load, which is a spherical pressure load. So this time it's PLOD-SPHR, like a sphere, which is used. So it could be used like the circle or the first example I show you to generate a round like this, except that it allows you to do some more complex shapes, because it can be also parameterized by different kind of angles. So to generate 2D or 3D wedges of a sphere that would be otherwise quite complex to model. So if you want to use this, the same in the side section, you use a sphere to create the geometry of the sphere, and in the plot section you use again a sphere. So if I come back to my analyst mode, this is exactly the same script. So except that in the side command now I'm using SPHR, like sphere, instead of cylinder, and same in the plot I'm using sphere. And this time this is a 2D model, so we are just seeing basically the same stuff than in the first example. But if it was a 3D example, then we would see it propagate like a sphere pressure. Okay, and that completes this video. So in the next video, we'll have a look at more types of loadings, like piezoelectric type of loads, and more advanced stuff. So thank you very much for watching. I'll put those examples in the description of the video so you can download them and try them by yourself. Thank you again.